Hello and welcome to Lesson 8 in the online terrestrial navigation course. Today's lesson is on Amplitude. As always, there's a worksheet in the description of the video you can download and follow along. There's also a couple of resources that you can download. It's the same Nautical Almanac excerpts and increments and corrections table that you used in the azimuth video. So if you still have those, there's no need to download them here. If you've not done the azimuth lesson, I would strongly encourage you to go back and master that lesson before jumping into this one. And before we go much further, I caught a little flack over the azimuth lesson about not really giving an explanation of what Greenwich hour angle and declination is. So let's take a 5,000 yard view of what exactly Greenwich hour angle and declination is, since you'll be using that in this video also. If we take a look at the globe with the lines of longitude and latitude on it, we're all pretty familiar with latitude and longitude, or at least we should be at this point. It's a grid system that we use to find a precise location. Now, the Earth has been described as a sphere within a sphere. When you go outside and look at the sky day or night, it kind of looks like a dome that's sitting over us. So that's known as the celestial sphere. And we take those same latitude and longitude lines and draw them on the celestial sphere. And we call those Greenwich hour angle and declination. They work the same way as latitude and longitude, basically, except Greenwich hour angle is measured all the way around the sphere to 360 degrees, where your longitude lines start over at 180 degrees and you have east longitude and west longitude. Incidentally, if you're doing a lot of home study, which I would assume you are since you're watching these videos, you may run across something abbreviated as RA, and that's in regular astronomy, where in navigational astronomy we use Greenwich hour angle. In regular astronomy they use RA, or right ascension, and it basically works the same way. It's just another grid system on the sky to give us a location of where that celestial body is in the sky that we're looking at, whether it be the sun, the moon, planets, the 57 navigational stars. We've got a grid system on that celestial sphere to tell us where that particular celestial body is, and we just call it Greenwich hour angle and declination. Now, if my graphic animation skills were a little better, I would have this illustration here spinning, but I couldn't figure out how to make it do that for this video. So maybe we can just imagine, if you would imagine this as maybe a spherical bird cage, and the globe is our little perch that we're sitting on there, and the stars are outside of the bird cage, and someone walks by the bottom, grabs it and gives it a spin. It would be like the Earth and the sphere are spinning, and the stars would stay still, and we would measure these stars where they're at on the grid system. And it's very important that we have precise time when we do this, because as the Earth is spinning in its rotation, those stars move across that grid system at a rate of about 4 miles per second. So when you're doing navigational astronomy, precise time is really crucial on that, because 1 second of time error can throw your final position off as much as 4 miles. And we'll get into the time tick problems and everything a little bit later, but you may have noticed the chronometer readings in these problems. They go down to the second and they make a big deal about chronometer error and how many seconds it's off. But again, 1 second of time error can land you 4 miles off on your positions or your LOPs by the time you do the work down. And we're just using this like we would use a lighthouse or a buoy or anything with a known position on a coastal chart, and coastal piloting, um, we're using these stars because they do have a known position. And you look up the known position based on the time. You look it up in the Nautical Almanac, and you've got a known position of that celestial body that you can use to draw an LOP. And I think this is where you start to get into the differences between a coastal pilot and an ocean navigator. Uh, when you're out on the ocean and there's no reference points anywhere to do any kind of bearings or get any kind of LOPs, anything like that, we can use the celestial bodies to get LOPs, lines of position, and things of that nature. So we're really crossing over that threshold from piloting to what I would consider actual navigation, ocean navigation. And these types of problems used to be reserved for just people who were getting their oceans endorsement on their license, but now the Coast Guard has decided to put these problems in the near coastal license. So even if you're going for a near coastal license, these types of problems will be on from 500 ton mate, 500 ton master, 1600 ton mate, 1600 ton master, third mate unlimited, and so on. Even at the near coastal level, the Coast Guard does test you on these types of problems. And this will give you really a pretty good solid footing. If you do decide to get your oceans endorsement, you'll already have a basic understanding of how this system works. All right, so without further ado, let's jump into the amplitude problems here. Let's take a look at exactly what an amplitude is. If you were on a road on the equator that followed the equator and driving off into the sunset at 270 degrees true, you might think the sun would be setting right there at the end of the road. Or if you were driving into the sunrise, you might think the sun would be rising at due east, 90 degrees true. But that only happens 2 days a year, and that's on the equinoxes in the spring and the fall equinox. Every other day of the year, the sun is either setting or rising north of west, or it may be south of west, or it may be north or south of east. But either way, an amplitude is a measure of how many degrees off of east or west that sunrise or that sunset is. And an amplitude can only be measured when the sun or any other celestial body is on the visible horizon as you see it here, or it can be measured on the celestial horizon when it's about 20 degrees above the visible horizon. And again, excuse my lacking skills in graphic animation, but here's what an amplitude on the celestial horizon would look like. There's a one extra step um, in the problems, depending on whether you take the amplitude on the visible horizon or on the celestial horizon, but we'll get into that as we start working the problems. Okay, so if we take a look at our first question here and we break down the anatomy of the question, you'll notice it looks a lot like the azimuth questions. They give us a date, 23 October. We have a DR position here, and we observe an amplitude of the sun. The sun center is on the visible horizon. That's an important part of the question here. We'll have a table 28 correction for visible horizon. It bears 259 degrees per standard compass. That lets us know that we're dealing with a setting sun. That's important here. And then it's not a rising sun. It gives us a chronometer reading and a chronometer error and the variation in the area, and it wants to know what the deviation of the magnetic compass is. Something you may notice here, it doesn't give us a zone time, but we can average that. Normally I would use, since we know it's a setting sun, um, we're at around 1830 local on a setting sun, and on a rising sun I would normally just average 0630 for a rising sun, because in an amplitude we do not deal with Greenwich hour angle, so the minutes and seconds part is not really as important as it is on an azimuth problem. We still need the minutes part, but it's not crucial in an azimuth work down. Um, so if we average 1830 for a sunset, take our DR longitude, and then we use that to convert this chronometer time to a Greenwich Mean Time, we can go into the Nautical Almanac with that. And this one converts to 23 October at 07 and 19 minutes, 18 seconds. If you're unfamiliar with that, go back to lesson 6 and look at converting chronometer time to Greenwich Mean Time, and you can pick that up from there. So with that date and time, we can go into the Nautical Almanac and we'll look for 23 October. Let's scale this out a little bit here and blow it up so we can read it. We're looking for 23 October and the 07 hour. And here we are, 07. And again, we only use the declination for amplitudes. We're not concerned with the Greenwich hour angle. And here our declination is south 11 degrees, 23.8 minutes. And we do need our little d correction. So as we scroll down this column, we see the numbers are increasing. So little d is going to have a positive 0.9. So let's put that on our scratch paper. And from here, we'll go to the increments and corrections to see what that little d converts to on the 19-minute chart in the increments and corrections. So again, we'll blow this up so we can see it, and we're working with 19 minutes. So we're over here and we're looking for 0.9, and that gives us a little d correction of 0.3. And again, we're finding the declination the exact same way we did in the azimuth problems. So we just apply that +3 to the declination here, and it gives us a declination of south 11 degrees, 24.1 minutes. Now the next thing that we need to look at is our latitude. Get our latitude from the problem, 21 degrees, 13.0 minutes north. And we've got another big scary math problem to plug into the calculator here. But it's pretty simple. We're going to do it the same way that we did the azimuth work downs. And these are the keystrokes here that we're going to use. And again, we're using the Texas Instrument 30XA calculator. This is just my little mock-up of it here. And we're going to key it in pretty much like we did the azimuth work now, except we don't have to use our storage, our memory on this one, because everything is just a one-time deal on this. So we'll put our latitude in and convert it to a decimal, 2113.0 to 1.130, second function, degrees to decimals. And then we need the cosine of that. So we'll hit cosine, and then we'll use this reciprocal key here, and we get this number. Then we multiply that times the declination, and we're going to key that in the same way, 11.241. Second function, degrees to decimals. Then we need the sine equals second sine. And this number that we come up with right here, 12.2, that's how many degrees off of due west. In this case, if we were working a sunrise problem, it would be how many degrees off of due east the sun is. So we are 12.2 degrees off of due west. Now we need to figure out, are we 12.2 degrees north of due west, or are we 12.2 degrees south of due west? And to do that, we've got a little diagram that we use. So we write down our correction as 12.2, and then we're going to, we know that we're dealing with westerly amplitude. So our amplitude, our starting number on a west amplitude is going to be 270 degrees, and we're 12.2 degrees off. Now, we need to know, do we add this correction or do we subtract this correction? And to do that, we're going to draw this little diagram here, and we're going to, you got to memorize this diagram for every problem. It's going to be the same. We've got a plus sign in the northwest, a minus sign in the northeast, plus sign in the southeast, and a minus sign in the southwest. And then we're going to look at our declination. Is our declination north or south? In this case, it's south. So we'll circle south. And then we look at our amplitude. Are we dealing with easterly or westerly amplitude? In this case, it's westerly. So our amplitude is either east or west. In this case, it's west, so we'll circle west. So we know we're in the southwest quadrant of this little diagram right here. So now this correction is subtracted. So we'll subtract 12.2 degrees from 270 degrees, and that gives us 257.8 degrees. So now that we have our amplitude is 257.8 degrees, because it's on the visible horizon, we have a table 28 correction. And this is table 28 here. In the exam room, you'll have a copy of the excerpts from Bowditch, and this table is on page 173 of those excerpts, and it tells you it's correction of amplitude as observed on the visible horizon right there. So if we blow this up a little bit and then look back at our problem, we see that our problem tells us it's on the visible horizon. So we go into this table with our declination degrees of 11 degrees. So it's going to fall right here between the 10 and the 12. And then our latitude degrees, the problem tells us we're at 21 degrees latitude. So we'll come down and it's going to fall right in here along this line. And then we can look right in here and we can pretty safely assume that our table 28 correction is 0.3. There is an equation that we could do in the calculator with this, but it's much easier to go to the table and get the correction than memorizing another equation for the lesson. So we'll just use this 0.3 right here. And again, we use the same diagram that we used to get the original amplitude. Our table 28 correction is a 0.3. And we need to do we add that 0.3 or do we subtract it? The way we do it is we look at our latitude is 21 degrees north, so we're at north latitude, and again our amplitude is westerly, so we're in the northwest quadrant of this diagram. So the correction is added to the 257.8, and it gives us 258.1. That 258.1 is the true bearing of the sun at that time, and now we just have a TVMDC problem. All the way back to lesson 1, we've got 5 degrees east variation. That gives us 253.1 magnetic, and our bearing is 259 per standard compass, so that goes here. That gives us a deviation of 5.9 degrees west. So it looks like our answer is going to be C.
Okay, the rest of the video is just working through the worksheet problem step by step. There is a curveball at question 27 and 28. I'll walk you through those when you get there. Other than that, just work through the worksheet. Try to score at least 90% on it or better before you move on to the next lesson. Don't forget to subscribe, give us a like and a share. Leave us any feedback in the comment section. I'll try to get back to you if you have a question or something on that. All right, thanks for watching.
Okay, question 27 and 28 are a little different from the rest. If you think back to lesson 1, we had a few problems that would give us a range in line at a certain bearing while the vessel was on a different heading. That's what's going on here. Is our amplitude bears 311 degrees per gyro compass while we have a heading of 352 degrees per gyro compass. And it's asking us for the gyro error and the deviation on that particular heading. So we'll use the amplitude to work down the gyro error, apply that to the gyro heading to get a true heading, and apply that to the magnetic compass heading to get the deviation. So let's take a look at how we do this. The first thing we're going to do is convert our zone time to Greenwich Mean Time. This particular problem doesn't give us a chronometer error, so we'll just use the zone time and convert that to Greenwich Mean Time, and that'll get us close enough for an amplitude work down. That would not work on an azimuth work down, but it does work on an amplitude work down. So we're going to go with 1955 Greenwich Mean Time on 20 June 1981. And now we just go to the Nautical Almanac for 20 June at 1955. We'll get our declination. 20 June looks like 26.3. So north 23 degrees, 26.3. And our little d correction is 0. So let's bring that up. PowerPoint's running a little slow today. Okay, the declination is north 23, 26.3 with a little d correction of 0. And again, my PowerPoint's not working like it's supposed to. And from this point, we just need our latitude, and we'll key all that into the calculator. The same formula that we've been using. And we will key in 52 degrees, 38.9, 2.389, second function, degrees to decimals, cosine, reciprocal, times the declination is 23.263, second function, degrees to decimals, sine equals second sine. Come up with 40.98 as the correction there. So we're going to round that to 41. We have north declination and west amplitude, so we're in the northwest quadrant of the diagram, so the correction is added. Gives us 311 degrees, and since this amplitude was taken on the visible horizon, we do have a table 28 correction. So we'll bring up table 28. We have a latitude of 52 degrees and a declination of 23 degrees. It's going to be pretty far down here. 52, 23, somewhere in this neighborhood here, between 1.1 and 1.3. So let's go with 1.2 for the table 28 correction. And we have north latitude and west amplitude. So that correction is going to be added. Gives us 312.2 degrees true. Okay, from here we can get the gyro error of 1.2 degrees east. Looking at our multiple choice answers, we don't have a 1.2 east. We do have a 1.3 east. So just a little bit of rounding error there. Our heading is 352 per gyro compass, so we're going to apply 1.2 east and get a true heading of 353.2. And now we can apply that to our magnetic heading to get the deviation. So our 353.2, and we're steering 358, comes out to 1.2 east. And a gyro heading of gyro error of 1.2 east. So it looks like D is going to be our answer on this one. Alright, with that you should be able to work through number 28, and after you do that you will have mastered the amplitude problems and be ready to move on to the next lesson. Don't forget to subscribe to the channel, give us a like and a share if you found the videos useful. Have any questions or comments, leave them in the comments section. Thanks for watching.